Hello and welcome to our project, an automated ureter anastomosis device by Team 5. Special thank you to our sponsors in advance of Texas Children's Hospital. Jackie is a beautiful newborn, however the day she was delivered proved to be not only the most joyous but also the scariest day of her parents' lives. Jackie was born with an obstruction in her ureters that caused an emergency surgery on her birthday. First, let's find out more about her complication and the field before we come back to her case. So ureters are extremely small tubes, so small that their openings are only 3 to 6 millimeters in diameter in children. As a result, it is very easy for these small tubes to become obstructed. This can happen for a variety of reasons, like congenital disease, urinary stones, tumors, or iatrogenic causes, which means they're the result of a more important treatment. When we understand the prevalence of this issue, we see it's something we need to fix. Ureteropelvic junction obstruction can occur in 1 in 500 live births. One pathology, hydronephrosis, occurs when a blockage in the ureters prevents urine drainage and causes kidney swelling. This can occur in 1 in 100 pregnancies. Newborns like Jackie, who are the 1 in hundreds, deserve the best fighting chance they can get. Currently, the gold standard for this treatment of these blockages is surgical treatment. After the surgery, of course, the two ends of the ureter must be sewn or put back together. Manual suturing is used, but it's extremely laborious and inefficient, especially in pediatric patients where time under anesthesia should be minimized. So what do we need? We need a surgical device that can automatically anastomose two ends of the ureters together using biocompatible, biodegradable, and anti-urinary stone materials to form a watertight junction. This will make these procedures more efficient and gives these newborns a better chance.
The stakeholders are crucial in understanding the user needs of our customers. The following stakeholders are taken into account. Infants and children. Our device will result in faster surgeries and better outcomes for these patients. Surgeons. Our device is easier on surgeons, causing less exhaustion throughout surgeries, and is automated to prevent human error and improve efficiency. For the healthcare providers, our device is a reasonably priced alternative that will reduce the need to follow up on patient complications. For the insurance companies, a minimized cost and efficient procedure will appeal to them, and they don't have to be concerned with having to fund another procedure from a post-operative complication. Lastly, the regulators and FDA approval of our device will make it more credible. The final user needs that the team use in tailoring the design inputs and design process to are as follows. Our device needs to fit through a 5mm laparoscopic port. Our device must completely degrade within 6 to 8 weeks, eliminating the need for a second removal surgery. The anastomosis junctions must be able to withstand the pressure of the flow of urine. There should be equal tension at all points of the coupler. Our device needs to be very specifically watertight and have non-loosening junctions. The material used shouldn't cause the formation of stones. And lastly, the device must be automated and faster than the traditional method of manual suturing.
Our user needs developed into our design inputs. To perform laparoscopy, the device must fit through a 5mm port. The device will be biodegradable such that it degrades within the 6 to 8 week healing period while fusing the tissue together. Making the device user-friendly by providing alignment markings and optional suture holes will simplify the device's implementation, and this will hopefully lead to shorter procedure times. Furthermore, 3D printing makes our device customizable and can be cost-effective. Moreover, the anastomosis mechanism must handle pressures during urine flow, ensure a watertight seal via the use of our fishhook design and interlocking prongs, and variable pressures can be employed with adjustable notches to prevent tissue necrosis or damage. And finally, material and cylindrical stent design will not result in stone formation or blockages.
As aspiring engineering students, we are strong proponents of the iterative design process and believe that our device, with the goal of automated ureter anastomosis, has also had several iterations leading to our most optimal form yet. Shown here is the old ureter anastomosis device we arrived at last semester. This device, as you can see from the simplified drawing, is already far too complex with several subsystems. Additionally, there is no customizability to account for different ureter sizes, and scalability is extremely difficult with so many micron-sized components. Due to these shortcomings, the device becomes error-prone from both a manufacturing and physician use perspective. After going back to the drawing board with our sponsors from Texas Children's Hospital and our departmental faculty, our new device is rather simple. At its most basic form, it is 2 nearly identical rings and a stent, shown on the top arrow and bottom arrow respectively. Still, however, we engaged in the iterative design process as you can see in the brainstorming drawing and in the development of the stent below. This device is robust and offers personalized care for the patient as it can be formed with molding or 3D printing. The simplicity of this device allows for cost-effective manufacturing and ease of use by the physician. With an understanding of this iterative design process, we can now talk about the specific details of the biocoupler device. As briefly mentioned earlier, the device features 2 rings and a single stent. In this overarching image of the process, on the left, you can see procedurally how the device works. First, the 2 rings are put on the ureter, and the spliced ureter is placed above the unique flanged stent. This stent, shown in light blue, is raised medially such that, as the ureter is pushed together, there is a region of tissue which can be linked together, known as anastomosis. With this exposed region of tissue, the 2 rings will be utilized to secure this junction. The biocoupler rings pierce through this tissue and lock into place. Finally, the system is in action, as shown at the bottom. Here the rings are locked to secure the junction and thus successful anastomosis occurs. Moreover, it is important to note that the entire system is biodegradable. Both the rings and the stent are made from PLGA, so the degradation rate can be tuned within the appropriate degradation timeframe of roughly 6 to 8 weeks. Focusing on the ring in particular, you can see that there are 2 rings with associated interlocking prongs. Inspiration for these prongs was derived from a barbed fishhook, which when piercing the skin of a fish is very difficult to remove. This model is better represented in the SolidWorks diagram shown here. You can see that there is a piercing barb and additionally 2 other levels of locking for adjustable pressure on the surrounding tissue. The barbed hook-like mechanism, when secured, resides in a protective hubcap to prevent lacerations from the sharp barb while implanted in the body. While not required at all, to make our device more appealing to early adopters, we have included suture holes in the biocoupler which are shown in lime green. Due to the decades-long predicate device of suturing, after consulting with our sponsors, we realized that including these suture holes could help surgeons feel more comfortable using a new technology. With respect to the stent, the design of the stent was iterated upon twice and finally led to the stent shown here. The medial gradient slope, or flange, allows for overlap of the ureteral tissue so that anastomosis can occur. Reinforcing the procedural steps mentioned is an animation and prototype hybrid video. With the rings already on top of the clear tubing representing the ureter is pushed onto the stent. With the region of overlapping tissue, the rings are pushed together as shown on the SolidWorks animation. Finally, as the system aligns, successful anastomosis occurs as the rings physically lock into place and create a secure fit.
In order to make sure we conform to our sponsor's degradation timeline, we performed a degradation study using 50-50 and 75-25 PLGA in both a 7.4 pH DPBS solution and a 12 pH NOH solution. Using FTIR seen on the right, we viewed the creation of hydroxyl groups in order to characterize the speed of ester hydrolysis of PLGA. By drawing parallels between the accelerated degradation study and the real time, we found that our target ratio should be somewhere near a 80-20 ratio. A more crystalline character of lactic acid, also making it easier to pierce the ureter. To physically stress test the leak potential of our device, we used a modified Mark artery demonstration, doubling maximum human systolic pressure of 100 milligrams of mercury. Not only did we find no difference in the flow, but we also found 0 leakage. Here you can see we have an average inlet systolic volume of 5 millimeters a second, and a systolic pressure standard for the ureter. Throughout the entire length of the stent, you can see that the flow volume never falls below 1 millimeter per second. Urine has a dynamic viscosity of 0.7183 centipoise, meaning this flow has a Reynolds number of around 9, far below the turbulent flow of 2,100, meaning no depositions or further kidney stones can form in such an environment. Because of the 23 nanometer roughness of PLGA, we do have dead zones on the shear of our stent. However, there is such strong flow reattachment such that there is no chance for even minor depositions to form along the stent. We could see that here in a particle deposition simulation. The flow detachment is so minor that not a single deposition forms, even in a hypothetical scenario where particles have been set to have an infinite affinity to PLGA.
Our future directions include our device's modification for use in the adult population via 3D printing's potential of customization. In vivo testing can be done to collect performance data to help us finely tune our device's performance. Live demos can be done to train surgeons in a clinical setting and get feedback on the device's ease of use. And finally, aiming for standardization in device manufacturing as well as setting a new gold standard in ureter anastomosis procedures will be achievable.
So this concludes our presentation on our automated ureter anastomosis device. We wanted to give a special thanks to our faculty in the Department of Biomedical Engineering and to our sponsors at Texas Children's Hospital. Once again, thank you so much.